My name is Melissa Rose. I am the manager of the Salt Technology section at Argonne National Laboratory, and today I'm going to talk about what the MSR campaign is doing in the experimental determination of molten salt properties. So obviously, we need reliable property data in order for the developers to design, license, and operate their reactors. And we need that property data to describe not just normal, but transient conditions as well across a range of temperature and salt compositions. And this will include the effect of contaminants and the accumulation of fission products as well. And not only do we need that data, but we need quality data that has been collected using standardized methods with known precision and accuracy so that that data can be used in the licensing process. Unfortunately, available data are often not sufficient or of an unsuitable quality, as most developers are considering salt mixtures other than MSRE. So we need to measure reliable property values for salts of interest. The main objective of this part of the MSR campaign is to generate high quality measurements of the properties of fuel-bearing molten salts to assist developers in this process. And sort of the steps we're going through to that are first to identify all of the quality affecting aspects of the property measurement techniques, their sensitivities, and the controls required to elevate them to NQA1 data quality. This will help us to assess the precision of our measurements and to distinguish the effects of uncertainty in a salt composition versus true uncertainty inherent to the measurement technique. We are doing that through the determination of property values of reference salts that we use to compare methods and determine within a lab repeatability, lab-to-lab reproducibility, and bias. This will lead to the development of consensus standard practices, which will be issued through ASTM-International. We will identify and generate a database of approved reference material salts, and all of the work through the round robin that Jake and Raluca have been working on is supporting these tasks. And then finally, we will be able to measure those fuel-bearing salt systems of interest using these consensus standard practices controlled at the highest level, and all of that data will go into the MSTDB for developers to access. So which properties are we measuring in the MSR campaign? Pretty much all of them, but I like to start with this picture. This is radionuclide transport and retention processes that were considered when generating source term models for a generic MSR. And it really points out all the different processes that these properties will have an impact on. Obviously, we need liquidus, solidus, boiling temperatures, vapor pressures, so that we understand what phase the fuel salt is in on all of the components within it. And that brings us to solubility, right? We need to know, are things plating out? Are they precipitating and suspending? Are they going to different areas of the reactor that were not where they're intended to go because they're insoluble? And we need to know that about both fission products and impurities from corrosion processes. We also, of course, need the more thermophysical properties, the heat capacity, density, viscosity. How is this salt going to hold and transfer heat? How is it going to move? We need to know how to size our vessel, how to size our pumps. So all of these properties go into that. And we are always open to learning about more properties that developers might need. So this list is a living list, and we are open to adding to it. So for those properties, what salts are we measuring? Obviously, we're targeting those gaps that Diane talked about in the MSTDB by measuring uranium and plutonium-bearing fuel salts. But first, we're starting with reference salts, like I talked about, so that we can optimize measurement methods, quantify our data quality. And so those reference salts are mainly FlyNac, FLIBE, and a sodium potassium chloride mixture. And I did want to highlight the round robin project that Jake started up with national labs and universities across the country. We're measuring aliquots of the same batch of FlyNac and sodium potassium chloride, and this will help us to quantify the reproducibility of several methods. When I started to prepare this talk, I surveyed my national lab partners in this area, and they helped me to create this lovely chart showing the different methods that are in use at the labs for measuring these properties. So you can see that, phase transitions and heat capacity across the board. The gold standard is differential scanning calorimetry. We've got a few different methods for solubility. In viscosity, interestingly, we're all using different methods, so that should result in very nice validated data. And then Some of these methods are highlighted in bold, and I will talk a little bit about how we're applying quality assurance methods to those later in this talk. All right. So obviously, our focus over the last year has been elevating the quality of our property data, and that involves determining what affects the quality of our property data and how we can assure it. So the main factors are, of course, salt composition. We need to know what salt we're measuring. The environmental factors, any instrumental uncertainties that exist, limitations analytically, and of course, the calculation method we're using for each technique. And the ways we can assure that, for salt composition, we need to know our reagent purity. We need to have carefully controlled batching procedures. For environmental factors, we need to control and monitor that atmosphere in the glove box or hood or wherever we're measuring these things. For limiting instrumental uncertainties, we need to use reliable measurement procedures and device calibrations, and this kind of goes back to developing those standard practices. For analytical limitations, we want to minimize those by using reliable reference and standard materials. And above all, we need to obtain a fundamental understanding of each technique so that we can be sure we're applying the appropriate and correct calculation methods. So here's just a couple tips on how we approach quality for each of these factors. For salt composition, we like to use batched compositions rather than measured compositions. Measured compositions tend to have a higher analytical uncertainty than, say, the balance you're using when you are actually measuring salts and mixing them. So that seems more accurate. For environmental factors, we require low and constant oxygen and humidity levels. We do identify and quantify all instrumental artifacts and uncertainties. We routinely check the calibration of devices and instruments, both complex instruments like the DSC and simple ones like calipers and balances. We do routine checks of measured responses with reference materials, particularly for devices that we cannot measure the individual artifacts. We can check their overall response with a reference material. And of course, we control chart all of those calibrations and checks over long times to check for instabilities. To limit or minimize analytical limitations, we always perform replicate analyses with replicate samples and then use reference materials to check proper operation. And of course, the most important aspect is being sure your calculation method has been assessed. So that involves identifying each quality affecting parameter and subjecting each one individually to calibration checks where possible, or using reference materials to do so for property determination. So now I'll kind of go through a few examples of how that quality assurance approach can be applied to some of the methods you saw on the table. So this is a hydrostatic method of measuring density. The basic idea is that you hang a bob from a balance and you measure the change in mass upon immersion, the delta M here in the equation. And so in order to apply quality assurance to this, you have to do it to each of the parameters in the equation. So for example, for the mass, we know the uncertainty of the balance. We can calibrate and check it. For the wire diameter, we use calibrated calipers. We can verify the temperature with a calibrated thermocouple. We can use established reference values for all of the constants. And then, of course, this equation also contains a surface tension term, and we directly measure that using this technique with two different bobs. I'll talk about that here on this slide. So we have determined over our many years doing this now, the surface tension, while neglected in literature frequently, is actually quite important to the value you measure. The surface tension is not insignificant, as some like to claim. So that is illustrated with the middle figure here for fly neck, where we took measurements in the red triangles with maximized surface tension effect, so a thick wire and a light bob. And then we took measurements with a thin wire and a heavier bob, the blue squares, which kind of minimize that surface tension term. And we were able to set those data points equal to each other because the density of fluid is the same, and obtain the surface tension value, and then back correct all the values to the real value, the orange circles. And we found that to be the most accurate way to quality assure the density values. Some other things to watch out for are preferential volatilization. Density measurements in particular take a long time, and if you have one constituent slowly volatilizing off, by the end of your test, you can be measuring a different salt than you intended. So that's something to watch for. Also, that salt can recondense on the suspension wire and affect the measurement in a dramatic way. And then lastly are impurities. So particularly beryllium oxide seems to have a large effect. You can see in the figure on the left, we measured FLIBE with a known 1 weight % concentration of beryllium oxide contaminant, and our data, while very precise, differs significantly from that in the literature. But also the literature values differ significantly. So it's clear that beryllium oxide contamination, which is hard to get away from with FLIBE, can be an ongoing issue, and impurities in general can be an issue we need to quantify. So when reporting salt data, it's really important to be measuring and reporting those impurity levels. And then the figure on the far right here is just some really nice precise density measurements we were able to do for uranium-bearing fluoride binary. This was actually the fuel salt for transatomic power. We had a gain voucher with them that was very productive, but unfortunately that company is no longer with us. They have allowed us to share that information with the public. So this is just a demonstration of the technique in action. I'll move on to differential scanning calorimetry, which is what we use to measure phase transition temperatures and heat capacity. So the general idea is that you ramp temperature at a constant rate and measure the difference in heat flow between your salt sample and an empty crucible. We do calibrate our temperature and heat flow readouts with metal standards. You can see an example of that in the top figure here, where we measured zinc. The intersection of those red and black dashed lines gives us the melting temperature, so we can calibrate that against a known value, and then you integrate the area of that curve to calibrate the heat flow of the instrument. We also only ever use heating data for our phase transition temperatures because we've observed significant supercooling with molten salts. So that's another quality affecting tip. We also try to use 3 samples to verify that the salt batch that we're looking at is homogeneous. And every sample is run at least twice to check system stability. And you can see an example of why that's important in the bottom figure on the right here, where we measured 3 samples of fly neck, and you can see their onset temperatures agree really well, indicating that the batch was homogeneous. But in sample 2, the dotted line and the solid line do not fall directly on top of each other, indicating that something occurred during the measurement of sample 2, which caused the system to be unstable. So we would discard those data for future use. And then the figure on the bottom left illustrates further what I was talking about with using batched masses versus measured masses for composition. So you can see that we measured 3 different compositions of this binary under the gain voucher, and they span a 0.5 mole % composition range. And you can see that the DSC is certainly sensitive enough to pick up the small differences in the shape and size of the eutectic and peritectic peaks. However, if we were to rely on our measured compositions, the typical uncertainty in the method we use is about 10%. So that equates to 2.7 mole %, which would mean these 3 samples would be indistinguishable from each other. So that's why it's so important to use a higher precision method of indicating your composition, so using the batched compositions. For heat capacity data quality, we've made some great strides forward this year. The basic method is that we use a reference material, a sapphire, and we do a comparative ratio method. So we measure 2 empty cells to establish baseline. We measure an empty cell versus the sapphire to get the delta phi ST here, and then we measure an empty cell in our sample to get the delta phi S. And through this equation, we're able to get the heat capacity of the sample. We have noticed that the measured CP is affected by a variety of things, some of which are listed here. Differences between the masses of the sample and sapphire need to be minimized so that first term goes as close to 1 as possible. And then the differences between the masses of the crucibles need to be minimized so that the effect of the crucible material is minimized as well. The figure on the top indicates why excluding the melt transition from your scanned temperature range when you're measuring heat capacity is so important. You can see in the green squares that we started at around 420 and scanned right through the melting point of fly neck, and that resulted in a depressed heat capacity value. Whereas with the blue circles and dark blue circles, we started above the melting point with a nice homogeneous molten salt, and we obtained a nice flat response, which was not depressed. We also discovered, as is illustrated in the bottom figure, that the stability of conditions in the DSC need to be closely monitored. Any instability at all can induce an artificial temperature dependence. You can see in the red data that there's a drastic positive temperature dependence, whereas when we ensure stable conditions in the DSC, we get a much flatter value. Now I'll move on to some viscosity measurements. So this is measured at argon using a rotating cylinder method. So the idea here is that we hang a spindle from the viscometer, which rotates it at a certain speed and measures the torque that it requires to maintain that speed. This method is only applicable if you have laminar, fully developed Newtonian cuvette flow. So this goes to applicability of the calculation method. So we need to ensure that condition. We also ensure all of the dimensions that we use in the equation are measured using calibrated devices, and we use a reference fluid to confirm proper operation. And I'll talk a little bit about that here. So these are just some examples of the silicone reference fluid measurements we've made with this device and how that helps us to ensure that we are observing laminar, fully developed Newtonian flow in the device. So torque measurements are collected at a variety of speeds so that we can confirm that Newtonian flow, that the relationship between M and N is a nice linear relationship. And then we also see that at a particular speed, we will actually get vortex formation starting and that behavior will change. So we can use the relationship of M and N to ensure that we are still in a laminar region. We've also noted that the calculated viscosity can be affected by things like the volume of fluid below and above the spindle, which can cause vortices or non-fully developed flow to occur. So the figure on the bottom here shows with a couple of different types of spindles that the amount of fluid between the crucible bottom and the spindle bottom, okay, the fluid below that spindle, needs to be sort of maximized to a certain value before you can get very accurate data. Otherwise, it's biased high. And another factor that can affect viscosity is impurities. If you start to develop undissolved solids, you get corrosion products, that can affect your measurement as well. So you need to control for that. And then I got these slides from Oak Ridge from Ryan Gallagher. Thank you, Ryan. And his team is listed here in the top corner if you have any questions about the particulars, but the basic idea is they're measuring the same property, viscosity, through a different method, a dynamic X-ray method, where a ball is dropped into a fluid-filled tube, and they measure the terminal velocity of that ball as it falls or rolls through the tube with X-ray radiography. And they can use the equation at the bottom left of the screen to determine the viscosity given the density of the ball and the fluid. Important to note here is that calibration factor K. So each crucible and ball combination is calibrated with NIST standards to obtain that K calibration factor. And that is used to correct for factors that may influence the measurement, but are difficult to correct for individually, like crucible roughness, the straightness of the tube, the ball roundness, which is why it is essential to obtain that K for each ball crucible combination. And of course, Oak Ridge is making replicate measurements to demonstrate the repeatability of the technique. And you can see that here, they've used 3 NIST calibration standards and made replicate measurements and are showing good precision. So our goal was to generate high quality measurements of property values of fuel-bearing salts to assist developers in designing, licensing, and operating MSRs. And to do that, we're identifying quality affecting aspects of property measurements and the controls needed to reach that NQA1 data quality level. We're determining properties of reference salts to assist in identifying repeatability, reproducibility, and bias in our measurements, and eventually working towards developing consensus standard practices through ASTM-International. The Office of Nuclear Energy, the Office of Science, the GAIN program, and Oak Ridge for submitting some slides for inclusion in this talk.
Thanks, Melissa. So could you explain how sample 2 is unstable in slide 11?
DSC is a very sensitive technique. So the reason for this instability, this difference between run 1 and run 2, could have been simply that the oxygen in the box changed. It could have been that someone was working a couple windows down from the device. It's really an environmental instability.
Elaborate on what is seen during cooling data during DSC measurements, which makes it unreliable.
Yes, so we see significant supercooling. So we will scan, up the temperature range and then down the temperature range, and we see a difference in the onset of melting between the two of upwards of 30 to 40 degrees. Sort of, if you look at the top figure here, that T onset for heating will be, say, here it's at like 425, but if we do cooling, it'd be more like 400, which is inaccurate.
What about fuel-bearing salts throughout their life?
Obviously, they're going to develop fission products, they're going to develop contaminants, and I think that's, once we develop these consensus standards through ASTM, I think we can then move on to more complex mixtures. Maybe that's where modeling can come in to help us with the addition of those impurities and their effect.
Do you use gold-sealed crucibles for the DSC?
Absolutely. We find that to be an important quality control factor.
So you mentioned impurity several times, as well as mentioning that some of these experiments take a while to complete. What sort of time are you talking about, and how do you control for salt attack on the nickel crucible? It sounds like you're using gold. I don't know if you use nickel or not. Do you?
We use nickel crucibles for some of our measurements, and we do watch for that. We do analytical measurements for trace impurities before and after, so that we can detect any entrance of nickel or iron or chromium or any corrosion products. So we do monitor for that and report it if we see it. We usually don't see attack nickel crucibles for the durations of these particular measurement techniques.
You said you do post-analysis, is that right?
That's correct, yes.
Yeah, so that was the other part of the question is, have you done post-test salt analysis to confirm the salt is within a certain range of purity from initial composition?
Absolutely, yes.
What's an approximate amount of spending by DOE on property measurements and predictive capabilities?
I think that's a question for Patricia more than me. I know what my budget is, but that's certainly not an all-in budget.
With that, we will conclude the chemistry session.